Hello. This presentation is on the use of ground-penetrating radar measured track conditions, and specifically ballast conditions, for the prediction of track geometry degradation. In other words, can I predict the rate of track geometry degradation and forecast poor track geometry condition using data taken from ground-penetrating radar measurements? And so this is a really important area in track maintenance because degradation of track geometry is a key area. And it's an area that every railway system, be it passenger, be it freight, has to deal with and has to plan geometry maintenance, be it surfacing, lining, whatever the key maintenance areas. So this research is looking at that relationship between measured ballast conditions and measured by ground penetrating radar type technologies and the ability to predict this rate of degradation and forecast when maintenance is going to be required. This work is based on an extensive set of track geometry and ballast condition data from major US Class 1 freight railroad in the Midwest. 6 sites were used here, 4 major geographical areas with multiple sites within each of the areas, and they were generally in the Midwest United States. The data was taken over a period of 2 years with frequent, every 2 to 4 week track geometry inspections. So we had of the order of 18 track geometry inspections for each site, plus ballast condition measurements by ground penetrating radar, again, multiple measurements. And as I indicated, we wanted to see, was there a relationship between the rate of track geometry degradation and these track GPR type measured parameters? And can we develop a predictive model? Can we actually develop a model to forecast rate of track geometry degradation? So very quickly, the GPR index values that we're looking at are the ballast fouling index, which is indication of the measure of fouling of the ballast, and the fouling depth layer, which is also called the free draining layer, which is a measure of how much clean ballast is there. So basically, as you can see here, the greater the fouling depth ballast value, it goes from 0 to 4, the less ballast we have, the less clean ballast we have. So really, if you have a good ballast layer, you're up in this range. And if you have a very shallow ballast layer, you have it up in this range. And the ballast fouling index, it increases in value as we get into the more severely fouled category. So again, the higher the category, the worse the condition, the higher the fouling index. And the index is based on research that was done years ago by Professor Ernie Seelig. So one of the first things we had to do was align the data. With 18 geometry runs at each site, data alignment became a real issue. As you can see, the before and after, this is 18 different runs. This is the same 18 different runs properly aligned. And the way we did this is we used a cross-correlation function to develop a lag or shift for between each inspection run, and then use this lag to shift each of the 18 runs and align them correctly. We did it actually in 2 steps, a coarse alignment and then a finer alignment. So the coarse alignment was of the order of a half mile, and the fine alignment was the order of 50 feet. Once we had the data aligned, we looked at what parameters should we use for the degradation of the track geometry. What is an appropriate value of the degradation of track geometry? And we focused on 2 parameters. One is the track quality index, which is a fairly standard measure of the overall condition of a specific piece of track. So for example, if we use a 300-foot window, which we used initially, we would calculate a track quality index as a standard deviation across the specific geometry parameter. For example, right profile or surface or profile, vertical degradation of the track. And we were able to calculate a TQI for each 300-foot window for each of the 18 inspections and plot them over time and look at the rate of degradation. And that's what this looks like. So this is standard deviation of right profile. Actually, this is standard deviation of all the parameters. So you can see, for example, right profile 62 is this black curve over here. So you can see degradation, some sort of maintenance activity, because ballast doesn't improve. The higher the standard deviation, the worse the ballast condition. So if the standard deviation decreases, it means the ballast gets better, which only happens if you do maintenance. And then you see this rate of degradation. And you can see it, as I said, for different parameters. But you have profile 124, profile 62, profile space curve, etc. The other parameter that we looked at, because TQI homogenizes the condition over this 300-foot window, so it doesn't find any specifically bad peaks. So if you have a bad peak like this one over here or like this one over here, it would get washed out a little bit over 300 feet. So to properly account for this, for these very high peaks, which are really the ones that you look at from a safety point of view, we also looked at the peak value over a 300-foot window. So we took a 300-foot window, and for each measurement run, we took the absolute largest value, minimum and maximum. We looked at both. And we did that for, again, for each of the 18 inspection runs over that period of time. And again, we plotted that with time, and this is what we get here. So this is the maximum and this is the minimum. Since geometry really degrades downwards, what we're really interested is the peak minimum, which is this downward degradation. So again, here you see the behavior, just like we saw with the TQI, we see in the peaks, there was initial degradation, there was maintenance. It's the exact same maintenance event we saw in the previous slide. And then we see the long-term degradation over this period of time. And for the rest of this presentation, we're only going to be focusing on the negative degradation. So we'll really be looking at this negative slope. So again, looking at one specific site, this is the H-fouled site. So this is the H zone, a 300-foot section of track that has foul ballast conditions as identified by GPR and the railroad. And you can see here again, the standard deviation, maintenance, and then the standard deviation increases. So the track gets worse, you do maintenance, track gets worse, fairly standard. This is time across here. This is about a 2-year period of time over here. So this is standard deviation, and this is peak. So again, remember peak or maximum maximum downward value or minimum value, if you want to take it that way. You can see degradation, the surface profile gets worse, maintenance, then degradation again. And in all these cases, we were able to get a rate curve. We actually used both a linear and a quadratic fit, but we found that the linear fit wasn't too bad. So going forward, we focused on using a linear fit going forward. So for example, you can see over here on this green line that we have a slope of about 0.11 here, and going down over here, we have a slope of about minus 0.21. So you can see it's a difference in slope because we're looking at a different parameter. We're looking at standard deviation over 300 feet here, and here we're looking at maximum peak. So when we looked at this site, and we looked at all the sites, as I'll show you as we go forward, the TQI profile showed an inconsistent increase before and after the maintenance event with a constant slope or a constant rate of degradation. So again, here again, constant slope before maintenance, constant slope after maintenance. The minimum data likewise showed a consistent degradation and a constant slope. So again, constant slope, constant degradation before maintenance, maintenance, where we improve, we bring it back up. You notice we don't bring it back up to 0 because track never gets back to perfection and only gets back up to a reasonably high value. And then we have degradation again with a constant slope of degradation. So when we looked at the left and right profiles, this was specifically right profile. If we looked at the left profile, it behaved similarly. If we looked at other segments of track, they behaved similarly, but with noticeably different slopes. For example, if we take that same zone, so first of all, here's the data we were looking at. So this is that track geometry data, the foul site that we were looking at in the H zone. So let's look primarily at the maximum value, the maximum rate of degradation. Before maintenance, there was a slope of minus 0.44. After maintenance, and by the way, some of the maintenance included some cleaning of the ballast, there was a slope of about minus 0.21. So there was a noticeable improvement in the rate of degradation, roughly cut in half by just doing that maintenance. However, if we went down the track and looked at what it was determined to be a clean section of ballast, in other words, where the ballast is very clean, just down the track, you can see, remember, you look from the milepost, we're only looking at several hundred feet down the track, and same traffic, same type of vehicles, same times, measurements were taken exactly the same time. And you notice that the slope was of the order of 0.11. So the rate of degradation for the clean ballast section was definitely better or slower than the rate of degradation for the foul ballast, even after cleaning. And notice for the clean ballast, the maintenance event really didn't do anything. The day rate of degradation was the same. We saw the same type of behavior with TQI, exactly the same behavior. Okay, after doing this, we decided we were going to expand the analysis, and we expand the analysis to look at the 4 study zones. Instead of using 300-foot lengths of track, we used between 45 and 65, average roughly 55 feet length of track. So we ended up with 250 segments, each segment for which we had 18 geometry runs. And so here you can see 120, I have 125 segments left and 125 segments right. So 125 segments left rail, 125 segments right rail, total of 250 data sets. As distributed over the 4 major zones. So real quickly, if we just looked at it very coarsely, what you see, the blue represents the profile, the worst profile. So you can see, for example, that here the profile is about the rate of degradation of the profile. So you can see here the rate of degradation is about minus 0.2 inches per year. Whereas over here, it may be of the order of 0.025. So there's about a factor of 10 difference in the rate of degradation between this location and this location. So what's unique about this location? Well, let's look at our ballast condition. This is my ballast fouling measure. You notice my ballast fouling measure is much more severe than the adjacent area. So where I have good ballast conditions, my rate of degradation is low. When I have poor ballast conditions, and a small ballast zone. So remember, the lower the free draining layer, the worse the ballast is, the higher the ballast fouling index, the worse the ballast is. You can again see there's a well-defined correlation between high rate of geometry degradation and poor ballast condition. This is for the P zone. We see the exact same behavior in the R zone. You can see this area here, high rate of degradation, poor ballast condition, high rate of degradation, poor ballast condition, high rate of degradation, poor ballast condition. The W zone, high rate of degradation, poor ballast condition. The H zone, high rate of degradation, poor ballast condition. So again, we're consistently seeing it on a broad level. Okay, so then we did several types of analyses to look at this. The first thing we did was a multivariate linear regression. We started off simple. And what we found, so this is a plot of the rate of degradation as a function of ballast fouling index. So there's my ballast fouling index. 50 is bad, 70 is worse, 10 is good. Rate of profile degradation. So again, negative slope. The higher the greater the negative slope, the greater the rate of degradation in inches per year. So this, for example, is minus 0.4 inches per year. So what this tells me is if I have a free draining layer of 6 inches, only 6 inches of clean ballast, which is this blue line, and I had a ballast fouling index of 50, my rate of degradation of my profile would be minus 3 inches per year, which is pretty significant, which means I'd hit 3 inches in a year, and 3 inches is usually where you do maintenance. So I'm degrading very quickly. This is the exact same information flipped. So I now plot again rate of degradation against free draining layer, and I use different color coding for my ballast fouling index, you get exactly the same value. If I look at a BFI of 50, which is this gray line, and I look at a free draining layer of 6 inches, I get the same minus 0.3 inches per year. And this is the actual relationship. This is the linear regression relationship. Doesn't make a difference whether it's left or right. The rate of degradation it gets worse with poorer ballast with more ballast fouling, and it gets worse when my layer of clean ballast is smaller. Again, both consistent with engineering logic. Okay, but we decided we wanted to do a little bit better than this. So what we ended up doing was we ended up doing a Bayesian regression analysis to calculate the rate of degradation. And when we introduced the Bayesian regression analysis, the first thing we did is we used the second order equation here. So you can see, for example, my Bayesian equation is related to the first and the free draining layer to the first power plus the free draining layer to the second power. Then the ballast fouling index to the first power, ballast fouling index to the second power, plus the cross term between the ballast fouling index and the free draining layer. And finally, we also introduced the last measurement. Because we are looking with measurement over time, we were able to introduce the last measurement value. And so that in turn gave us an additional value in predicting the ability of the track to degrade. And what that gives us is a relationship that looks like this. Okay, so here we can see two sites, a foul site and a control site, both starting off in less than perfect conditions. But you can see the rate of degradation for the foul site is more severe than the rate of degradation for the control site. The foul site reaches a 2-inch profile limit in 3 years, while the control site, which has the exact same traffic and the exact same measurement types, reaches that same 2-inch limit in 4.5 years. So you can see the foul site degrades more rapidly. This is consistent with what we're seeing here with this Bayesian equation. And again, it really supports the final results that we obtained here. So to summarize, we produced a comprehensive study of 6 major test sites encompassing 4 study zones in the Midwest US, looking at a broad range of ballast conditions, looking at multiple track geometry measurements, roughly 18 measurements in 2 years, and multiple GPR, ground penetrating measurements at the same time. And we developed a relationship between significant track geometry degradation and 2 key GPR parameters: fouling ballast, how foul is the ballast, and fouling depth layer, how much clean ballast do I have? And the results show a very well-defined relationship between high rates of degradation and poor subsurface conditions, and it actually allow us to develop a series of equations that will allow us to forecast the rate of degradation, which in turn allows us to forecast when the track is going to degrade to the point where it exceeds a standard value, and then and for which maintenance is required. So you can see maintenance is required at the minus 0.2 here. And again, you can see the point of maintenance is much earlier for the foul than the control. And we can see this for all different sites that we're looking at. I'm out of time. Let me acknowledge the support of the U.S. Department of Transportation, Federal Railroad Administration for this research, with special thanks to Mr. Hugh Thompson and Dr. Ted Sussman. Thank you very much, and I hope you found this to be of interest.